All right, this is lesson 3.2, everything you ever wanted to know about polynomial functions. So go ahead and have your notes packet out in front of you, and we're going to go ahead and get started. A monomial is a numeral, a variable, or an indicated product of a numeral and one or more variables. What this means for you is that nothing is being added or subtracted with this monomial. Remember that mono means one. So we've got some examples below: 2m squared, 4ab, 9x cubed, y squared. Those are all examples of monomials. When we're looking at a monomial, specifically a times x to the n, the number denoted by a is what we call the coefficient. Of our variable. The symbol x to the n represents a power of x, where x is called the base and n is called the exponent. A monomial with no variable, such as the number 9, or -6, or in our first example, 2, we call that a constant. The degree of a monomial is the exponent n, and this is going to be especially important for us in this unit. If the monomial contains more than one variable, the degree of the monomial is then the sum of the exponents. So let's go ahead and take a look at this first example. We have 8a squared b to the 4th. The degree here is actually going to be 6. That is the sum of both the powers in those variables. A has a power of 2, B has a power of 4. Since they're being multiplied together, we're going to go ahead and add them. The coefficient is 8. So when we take a bunch of monomials and we put them together, a sum of monomials, or maybe a difference of monomials, that is what we call a polynomial. The monomials of the expression are called the terms of the polynomial, and the coefficients on each term of the polynomial are the coefficients of the polynomial itself. The degree of a polynomial is the degree of the term with the highest degree. So let's take a look at a couple examples. Starting with number 1, the degree here, since 7 is the highest power, this is a 7th degree polynomial. The coefficients, we're just going to go ahead and list out in the order that we see them. 5, -9, 6, and -22. Taking a look at number 2, this one's a little bit different because we have 2 variables within each of our terms. So take a second to look at that and make your prediction. The degree here is actually 6. If we look at the first term, I have a to the 5th and b. That makes that term have a power of 6. The second term, a squared and b squared, yields a power of 4. And the last term, a times b, is a power of 2. So we're again going to go with the highest power amongst those terms. The coefficients, 3, -3, and -9. Talking more specifically about what these polynomial function graphs look like, they are defined as being both smooth and continuous. By smooth, what we mean is that the graphs contain only rounded curves with no sharp corners, meaning those absolute value functions that we just talked about, not going to cut it for this unit. By continuous, we mean that the graphs have no breaks, and ideally, they can be drawn without having to lift up our pencil from the paper. This next piece is probably where we're going to be spending quite a bit of time for the next few minutes here in our notes, talking about end behavior of polynomial functions. So the end behavior of the graph of a function, we're talking about to the very far left towards negative infinity or the very far right towards positive infinity is what we call its end behavior. Although the graph of a polynomial function may have intervals in between where it increases or decreases, eventually our graph is going to rise or fall without bound as it moves far to the left or far to the right. So the sign of the leading coefficient along with the degree n of our polynomial are the two pieces that reveal the function's end behavior. So we've got a really mathy, technical definition straight from your textbook that defines this leading coefficient test. It says as x increases or decreases without bound, the graph of the polynomial function, this is just an example of some polynomial function, eventually rises or falls. In particular, the sign of the leading coefficient and the degree of the polynomial reveal its end behavior. There is a really nice visual of this on page 350 of your textbook. It's a little bit heavy, so I decided to leave it out of your notes, but we're going to simplify that table. Maybe take a look at it tonight when you're working on your homework and kind of compare what the textbook shows as examples for end behavior versus what we are about to do in the box. So, we've got two options for end behavior. We're either going to talk about the degree of our polynomial being odd, or we're going to talk about the degree being even. For an odd degree polynomial, you've got a little space up here. I want you to write a little note to yourself. Think about the function f of x equals x cubed. That is one of our favorite odd functions. It reveals information about symmetry. Remember that odd functions have origin symmetry. It's also going to help us remember our end behavior. Similarly, over here in the second set of boxes for an even function, we're going to think about f of x equals x squared. And this is all going to make a little bit more sense here in a couple minutes. So, within this odd degree polynomial, notice that our box is split into two. We have two options. We're either going to have a positive lead coefficient, I'm going to abbreviate coefficient here, or we are going to have a negative lead coefficient. And what this is going to look like, notation-wise, we are talking about A being positive, and then our power being odd, versus something like this. F of x equals negative A times x to some odd power. And remember, when I'm writing this, there are other terms associated with this function, we're only talking about the lead coefficient in that very first term. So over here on the left, if my lead coefficient is positive with an odd degree, my end behavior is going to look like this. I like to just draw it. We would write this as falls left, rises right. In the column that we have marked for a negative lead coefficient, we're actually going to be doing the opposite. We would write this as rises left, falls right. And the reason I had you write down f of x equals x cubed is because this is my favorite way to remember this end behavior. X cubed is a really basic odd function, meaning it has an odd degree. So if we just sketch a quick graph of what f of x equals x cubed looks like, this is going to help us remember that when it is positive as a lead coefficient, I'm down on the left and up on the right. Now over here, if I were to turn that into a negative x cubed, we know from our transformations that that is a reflection over the x-axis. So my graph actually is going to look like this. And we can see that it's now rising on the left and falling on the right. So let's apply this same idea for our even degree polynomials. If my lead coefficient is positive, and I'll abbreviate lead coefficient with LC, that would look like f of x equals a times x raised to some even power. In the case that my lead coefficient is negative, that is going to be f of x equals negative a times x raised to an even power. For a positive lead coefficient, my end behavior rises left, rises right. And for a negative lead coefficient, we're just going to flip that. Now we fall left and fall right. And again, our favorite even function, f of x equals x squared. If we do a quick sketch of that, we know what a parabola looks like. Notice that the end behavior is up on both sides, but as soon as I stick a negative out front and make that negative x squared, we are going to reflect that parabola over the x-axis, and you can see that my end behavior is down in both directions. So for our last example on this page of our notes, we're going to take a look at what some of these look like in determining end behavior. This is just one part of the puzzle when we're trying to figure out what these polynomial functions look like. And what we're doing right now is we're building up a bunch of tools that we can use to piece everything together at the end.